Hello and what's up, amazing people, students, lovers of chemistry, and all my amiable subscribers out there on YouTube and all the other platforms that we are on. I'm so excited to be here with you on yet another episode on electrolysis that we started some time ago. And in today's episode, we want to look at the Faraday's laws of electrolysis because these concepts are very, very important if you must grasp the concept of electrolysis. So let's get into what we have for today. First of all, what are the Faraday's laws of electrolysis? These are laws that help us to calculate how much of a substance is produced at an electrode during electrolysis. Now, let's backtrack a bit. In the introductory part of this series, we talked about what electrolysis meant, and we said it is the process whereby we use electricity to break down a substance. Now, when a substance is broken down, the substance that is broken down is liberated at a position called an electrode. So it is through Faraday's laws of electrolysis that we get to calculate and find out how much of a substance was liberated at an electrode. Now, that brings us to the next thing that we want to talk about and explain, which is Faraday's first law of electrolysis. Now, that law states that the mass of a substance produced at an electrode is directly proportional to the quantity of electricity passed. So in simple terms, what the first law of electrolysis according to Faraday says is the more electricity you have, the more substance will be formed or produced. Now, there is a mathematical side to it, which is very, very important. But before we talk about that, let's move to the Faraday's second law of electrolysis, see what it means, and then address the individual formulas one after the other. Faraday's second law of electrolysis states that when the same quantity of electricity passes through different electrolytes, the mass of substances produced is proportional to their chemical equivalents. Now, mathematically, what we mean when we say the Faraday's second law of electrolysis is the mass of a substance M is equal to its molar mass multiplied by the current in amperes I multiplied by T time in seconds divided by the number of electrons involved in the reaction multiplied by the Faraday's constant. So in simple terms, what the second law of electrolysis according to Faraday says is heavier atoms or ions need more charge to be deposited. Now that we've talked about what the two laws entail, let's talk about some of the important terminologies that you need to familiarize yourself with so that you can get the hang of what we want to talk about in today's video. The first term is the term called charge. Now, in electrolysis, we denote charge with the letter Q, okay? Because Q there stands for the quantity of electricity that is used. All right, so that's why we use the letter Q. And it is known as the electricity passed in coulombs. Okay, and the unit for coulombs is the capital letter C. The next terminology is current, I, and it is measured in amperes, denoted by a capital letter A. The next one is time, T, and it is measured in seconds, and it is denoted by the letter S. And then we have the last one, which is Faraday's constant, F, and it is denoted in coulombs per mole. And it has a value of 96,500. What this simply means is that you need a charge of 96,500 coulombs to be able to move 1 mole of electrons in the process of electricity. Now, this means that 1 mole of electrons carries 96,500 coulombs. Pretty massive, right? Now, so here are some basic formulas you need to remember. For the Faraday's first law of electrolysis, the formula states that Q, which is electric charge or the amount of electricity passed, is equal to I, which stands for current, multiplied by T. You can see it denoted over here. Charge is equal to current multiplied by time. And then the next formula you need to be familiar with is mass is equal to number of moles N multiplied by molar mass mm. You can see it over here. Mass is equal to number of moles times molar mass. So now that we have familiarized ourselves with some of the basic things we need to know, let's deal with a few questions. One for the first law of electrolysis, another for the second law of electrolysis, and then we'll call it a day for today's video. Example number 1 says a current of 3 amperes flows for a period of 10 minutes. What is the charge that is passed? Now we know that the formula states that charge Q is equal to I, which stands for current, multiplied by T, which stands for time in seconds. So let's get our parameters listed out so we can impute them into the formula and then get our answers laid out correctly. So we have Q, which is unknown. That's what we're looking for. I stands for current, and in this case they've given us the current to be 3 amperes. Remember, current is measured in amperes. And then we have the next variable, which is time. Time was given to us as 10 minutes. Now remember, in the concept of electrolysis, we measure our time in the unit of seconds, not in minutes. So we need to do a bit of math by converting these minutes over here to seconds. How do we do that? You simply multiply by 60. So when you multiply the figure of 10 by 60, you end up with 600 seconds. So having done that, let's impute our variables into our formula and come up with our answer. So Q is equal to I multiplied by T. I here is 3 amperes multiplied by T, which is 600 seconds. So therefore, this is equal to 600 multiplied by 3 gives us a figure of 1,800 coulombs. Okay, you can write it either like that or you can write it like this, whichever way you please. It's absolutely fine. So you can see how the first law of electrolysis was used to calculate the amount of charge that was involved in an electrochemical reaction. So now we've seen how the first law applies. Let's go ahead to check out how the second law applies. The second question asks us saying, how much copper is deposited when a current of 2 amperes passes through a solution of copper 2 tetraoxosulfate 6 for 30 minutes. Now they've given us all the details we need to know. We have the electrochemical reaction, we have the molar mass of copper, and we have Faraday's constant. So let's see how each of these variables come to play, and let's solve the question step by step. Alright, so the first thing that needs to be done is that we need to outline the formula to be used. Now we're looking for the mass of a substance deposited, which lets us know that we need to use the formula that applies to Faraday's second law of electrolysis. And that law has a mathematical formula that says the mass of a substance M is equal to its molar mass multiplied by the current in amperes multiplied by the time taken T in seconds divided by the number of electrons involved in the reaction multiplied by Faraday's constant. So let's impute our variables into this formula. M is equal to, capital letter M stands for the molar mass, and in this case we have the molar mass of copper to be 63.5 multiplied by I over here stands for current in amperes, and we have the current to be 2 amperes multiplied by 2 multiplied by, we have T, which stands for time in seconds. Now in this case we have our time to be 30 minutes. So 30 minutes combined or converted into seconds becomes 30 multiplied by 60. We'll do a bit of math. 30 multiplied by 60 gives us a figure of 1,800 seconds. So we have 1,800 over here. And then over here we have N. N stands for the number of electrons used in the reaction. Now we have the equation of the reaction to be Cu2 plus undergoing reduction, combining with 2 electrons to give 1 mole of copper. So you can see it has been denoted over here that 2 electrons are involved in the reaction. So we have a figure of 2 here multiplied by Faraday's constant, which is 96,500. So doing that, we have M is equal to, so let's get the figure for the numerator over here. We have 63.5 63.5 multiplied by 2 multiplied by 1,800. We have a figure of 228,600 divided by 2 multiplied by 96,500. That gives us a figure of 193,000. So now that we have that in place, let's do the division real quick. We have 228,600 divided by 193,000. That gives us 1.185 grams of copper deposited. So the question asked us what is or how much copper is deposited, and we've calculated it to be 1.185 grams of copper deposited. So I'm sure you saw how the two laws are applied. The first law is used for calculating the amount of charge or electricity involved in an electrolysis or electrochemical reaction. The second law, or Faraday's second law of electrolysis, helps us to calculate the mass or the amount of a substance deposited or liberated at an electrode. I want to say a very big thank you to each and every one of you who stuck around till the end of this video. It's been an interesting bit for me sharing my insights on chemistry with you, and I'm sure you enjoyed it. If you did, please like, share, subscribe, and do well to turn on the notification bell icon so when more bangers like this are dropped, you will be the first to be notified. Up until I come your way next time, my name is David, and all we do here is to take the mystery out of chemistry so Chemi can make history. I will see you in the next video.